So I've got a scenario here where we'd like to find the Lagrange interpolating polynomial that passes through these 3 points. So what makes this question a little interesting is I picked those points very carefully. If you look closely at them, you'll see that they are, in fact, linear. They're all on the line y equals 2x. So what we've seen in the past is that the polynomials we've gotten from this Lagrange interpolation method have always been 1 degree lower than the number of points. So we're kind of expecting a second degree polynomial here, but I'd like you to think for a minute, and obviously you'll see the result in a second, but I'd like you to think for a minute whether or not that's even possible. All right, so we're going to go through the process here and just kind of see how the method handles this somewhat unusual situation. All right, so I've got our general formula up there, and I'm going to have 3 of these sub-polynomials, 1 for each point. And I've got the first one here. You remember how we do this. We're doing this for the point 1, 2, and the numerator is made by taking x minus the x coordinates of the other 2 points. And to get the denominator, we take really those same 2 factors and replace the x with the x coordinate of the point that we're working on. Right, so the denominator becomes 1 minus 2 over 1 minus 3. Now, I encourage you to pause the presentation, try to work through that for the other 2 polynomials, right? See if you can get those. Then you can start it back up again and see what I ended up with. So here's my second one, right? We're basing this on the second point, the 2, 4. So I've got x minus 1, x minus 3 in the numerator, the x coordinates of the other 2 points. And I've got 2 minus 1 and 2 minus 3. I replaced the x's in the numerator with 2, which was the coordinate of the second point. This is the one we're building off of. And then finally, we get this for the third polynomial. Okay, so if we simplify these, right, I'm going to multiply them out. I'm going to simplify the bottoms. The bottoms all just become numbers. We end up with these 3 sub-polynomials. Right now, I'm running out of room a little. So I've got our 3 sub-polynomials here, and I've got the final result that we get once we combine those with the y coordinates. Remember how we do this. Right, I'm going to take the y coordinate from the first point. I'm going to multiply it by the first of our sub-polynomials, and that gives me the first term. Then I take 4 multiply it by L2, 6 multiply it by L3, and we get our final result. Okay, now on the next step, I'm just going to simplify all the numeric parts. The 2's cancel on the first one. 4 divided by -1 is -1, so that just reduces the sign of those 3 terms. And of course, 6 divided by 2 is 3, and then I distributed that into the x squared minus 3x plus 2. And this I'm feeling good about. If you look at the x squared terms, x squared minus 4x squared is minus 3x squared. Add 3x squared to that, and you get 0, and the x squared terms go away. And if you look closely, the constant terms do the same thing. So in the end, all we're left with is p of x equals 2 of x for our interpolating polynomial, and that's awesome because it's exactly the one that I used to generate those points. So this is actually a really good result for us. This kind of suggests that this method is what we would call robust, right? Which in plain English means it's not easily fooled. If you throw it kind of a weird situation, like 3 points that are colinear, it handles that. It doesn't give us some weird quadratic polynomial, which wouldn't actually work. It doesn't kind of choke and give us no answer at all. It gives us the very reasonable lower degree polynomial, if you will, that we would expect. So real quick, just to see why there clearly couldn't be a quadratic result here, just by knowing that those points are linear, are colinear. To get from the second point to the third point, the y coordinates would have to increase at a quadratic rate relative to the change in the x values. And we know that they don't. We know that they're only increasing at a linear rate. Right? So there's really no way this could have ended up being a quadratic polynomial. So if you'd like to see the context, the link at the bottom here will take you to the lecture where we actually kind of work through deriving the formula for those subpolynomials. Or you can click on the link here that'll take you to the next lecture. It's a little more on the theoretical side. We're going to take a look at coming up with an error bound for these Lagrange polynomials. And of course, if you like this presentation, please don't forget to click on the like button down there on the bottom as well.